Good afternoon and good morning. I'm Rakshith Krishnappa. So I'm from Intel, work as a developer evangelist for oneAPI, mostly focused on high performance computing. So I will be leading this three-part series on performance, portability, and productivity. So let me quickly show you the details about the series. So it's mainly a three-part series, and we also have a optional fourth part, which is more like a hands-on session and hackathon. So the three sessions will mainly focus on the first one is mostly an introduction to performance, portability, and productivity. And mainly this will set the stage for how to optimize your code and how to achieve performance portability across CPUs and GPUs. So that's what we will be doing today. And next month, it will mainly focus on optimizations and best practices using SYCL programming. And the third part will mainly focus on optimizing for performance portability across CPUs and GPUs. And like I said, the fourth one is an optional like a placeholder we have so far. We want to see if there's any interest for people to bring their own code, and we will have a bunch of Intel experts in various fields, and we will help you with any optimization or performance portability. Or if there's any topic someone suggests they want to get more details about, and that's what this fourth session will be used for. Okay. So what will you be learning in this learning series? So in today's session, mainly we will understand why performance, portability, and productivity are important for high performance computing. So to understand that, what we will do is we will identify algorithm that we will use as a test application, and we will implement this using the Math Kernel Library, and we will check for performance on some CPUs and GPUs on the DevCloud. And we will, once we have this solution using a library, we will also try to implement the same algorithm using like basic SYCL programming, right? Because mainly we do this because not all algorithms that you may be developing has a direct library available. So in some cases, you do have to write your code from scratch, and that's why we try to do both the approaches. And then once we have these two solutions, we will analyze the results using Intel Advisor Roofline and also the Intel vTune Profiler. And we will, capture some numbers and then see how it compares the two solutions that we have. And we will do all this on Intel DevCloud. So hopefully everyone's registered for a DevCloud account. It should only take less than a minute. If you haven't registered, we will walk you through. So mainly what this will give you is access to a bunch of hardware that you can use to run your code. So all the compilers and tools are already installed on DevCloud. So all you have to do is register, and then I will walk you through how you can access it and start using these different hardware. So mainly the hardware that we will be using are we have two GPUs, the Gen 9 integrated GPU, and then we also have the Iris Xe Max discrete GPU, and then we have two different Xeon processors that we will be using. So one is the Gold Xeon Gold processor, which is I think it's an 8-core processor, and then we also have the Xeon Platinum, which is a 32-core processor, right? So we have a various mix of hardware, two GPUs and two CPUs with different characteristics, and then this is what we will use to measure performance, and then eventually in the next sessions we will work on optimizing to achieve performance portability across these platforms. right? So that was today's session, and next month mainly we will focus on um, how I mentioned that we will be writing a basic SYCL code from scratch. So we will work on tuning this algorithm, the basic algorithm, using various features of SYCL. We'll mainly learn about ND range kernels and the impact of workgroup size, and we'll try to use some of the low-hanging fruit to optimize the code, like how to use private memory and then how to use shared local memory to improve performance. So typically using these approaches will uh, get you significant performance. We will look at that, and again we will analyze the results using Intel Advisor Roofline and also Intel vTune Profile. So that's next month, and this should be more interesting. And in the third part, so this is where we will actually optimize the algorithm for performance portability, so that we can get performance across both CPUs and GPUs. And once we've done that, we will try to analyze all the algorithms we have implemented so far, and then try to compare all the results. And we will also next understand the hardware characteristics and further optimize, right? So we'll try to understand what are the differences in GPUs versus CPUs, and then how to write your code so that the performance actually is portable across all the different accelerator devices. We will understand the impact of accelerator occupancy and also the impact of varying workgroup sizes. And finally, we will also look at some resources for more advanced tuning using the oneAPI GPU optimization guide. So this is more of an advanced topic. So we will just introduce you to this guide and how to navigate through this one to further optimize your code. Right, and then finally, the fourth session is a mini hackathon working session. So you can either bring your own code. If you can share it, you can share it, or you can also work one-on-one with some Intel experts. We will have various breakout rooms set up, and we will have Intel experts, hopefully in all the different fields, hardware architecture, some SYCL language experts, performance tuning experts, and also tools experts, right? So this is a good session to take advantage of, if you're working on some code using data parallel C++. Right. So with that, let me just start with a brief introduction, and I would like to keep this session more interactive and then more hands-on coding. So I will quickly go through some introduction, some important slides, and then we will jump into Intel DevCloud and start programming, right? So mainly to understand the reason for this whole solution. So let's understand the programming challenges for multiple architectures, right? So usually, if you want to program for a CPU, GPU, or accelerator, any other accelerator, you typically had to learn different programming languages, had to use different tools for different hardware, right? And this was a problem, and that's one of the reason a couple of years ago Intel introduced the oneAPI industry initiative. So mainly it's a set of programming languages, tools, and libraries that work across all the different hardware, CPU, GPU, FPGAs, and other accelerators, what we call the XPUs, right? So mainly there are a couple programming languages like data parallel C++, OpenMP, Fortran, that now actually work whether you want to program for CPU and as well as GPU, and the same thing with tools which are the same vTune profiling tool will actually work whether you're trying to profile a CPU or a GPU. And these are the set of tools and languages that are available in the oneAPI toolkits that are available, right? And in today's session, mainly we will focus on data parallel C++. Mainly this is a standards-based cross-architecture language. It's mainly based on C++, and then the SYCL standard for heterogeneous computing, right? It's a community-driven project. Anybody can, submit a pull request and then, develop new features, but it's mainly based on the SYCL specification, the latest SYCL 2020 specification, to be specific. Right. So if you want to learn more about data parallel C++, we have another learning path series called the data parallel C++ Essentials Learning Path. So the link for this is available here. I mean, these slides will be shared, I guess, and you can look at this link, which mainly assumes people only know regular C++ and tries to build on top of that to introduce you to data parallel C++ and how to offload tasks to like GPUs or any other accelerator. So we have been, I think most of you might have actually gone through these learning series. We have been presenting this over the last 2 years. For people who want a book, there's also a free download for a data parallel C++ book that's available, which also starts from the basic and also goes into some details about tuning. And finally, there is the oneAPI GPU optimization guide, and this is more of an advanced content, which guides you how to optimize your code for GPU. Based on different kind of GPUs that we have. Right. So with that, and like I said, the data parallel C++ compiler is mainly based on the SYCL 2020 specification. So the specification, the link to the specification is right here. So before I jump into the actual coding samples, I wanted to quickly give an update about the compiler. A lot of people might have been using the data parallel C++ for the last 2 years, and in the recent release, it's been updated to use to follow mainly the SYCL 2020 standard. So we will look at what changes have been made so far in the existing, the released compiler currently. So mainly the SYCL 2020 specification was released earlier last year. So some of the major features of the 2020 specification are, unified shared memory, reductions, modern atomic subgroups, group algorithms, and extensions and interoperability mechanisms, right? So most of these features were already available in the data parallel C++ compiler. It was available as extensions. It wasn't part of the standard before, but now these features have been moved into the SYCL 2020 specification. So some of the syntax has changed since the last time you've used. So that's what I wanted to quickly go over. So many of the extensions have now become part of the SYCL 2020 specification. So some of those examples are unified shared memory or USM, subgroups, and reductions, right? And the compiler now adopts the SYCL 2020 syntax for these features, right? So this is a quick snapshot of unified shared memory and the different types of memory allocations, malloc_device, malloc_host, and malloc_shared. So if you have used this before, it's still the same. Nothing has changed in unified shared memory. Going into subgroups in SYCL 2020, so you might have noticed if you were using subgroups before in the data parallel C++ compiler, this is how you would get a subgroup handle. For example, we used to get the subgroup handle in the SYCL oneAPI namespace, or it used to be like SYCL ext and oneAPI. So now, since this is in the SYCL standard, you would actually get the subgroup handle by just directly SYCL colon subgroup, right? Or you can just say auto, and that's another way to also get the subgroup handle, right? And same with in data parallel C++. Before, we introduced to subgroup shuffles, which are now part of SYCL 2020 subgroup group algorithms. These are available as free functions instead of member functions. So before in the data parallel C++, we used to have these shuffle operations like shuffle down, shuffle up, shuffle, and shuffle XR. And in the new compiler, we follow the SYCL 2020 format, which is in the it's a slight rename. It's now called shift underscore group underscore left, and then shift group right, or select from group, or permute group by XR, right? So again, you can see that it's a free-form function under the SYCL namespace. And mainly, the main thing what the SYCL 2020 committee decided was, since these functions are applied on a group, right? It could be either on a subgroup or a work group. So the word group is actually included in all the function names. So that's the main difference. And also we had a bunch of subgroup collective functions, which are again now called SYCL 2020 subgroup group algorithms. And again, you can see that before we used to call it broadcast, and now it's called group underscore broadcast. Reduce has now become reduce over group. So same thing, we have this word group added to all of these functions, mainly because it's more clear for people that these are applicable to actual groups, right? Whether it's subgroups or work groups. And going into reductions, so this is again was introduced as a oneAPI extension before. We used to use like SYCL, ext, oneAPI, and reduction. And same thing for the operator. We used to use a different namespace. And now these are all part of SYCL 2020 specification. And that's and now you would actually directly, it's available in the SYCL namespace. And this is how you would do reductions in the latest compiler, right? And again, a quick comparison. In the old, we had two approaches for reductions, whether you're using USM or buffers. Before, we used to have this a different namespace, ext, oneAPI, and reduction. So now it's just SYCL reduction. And the main difference with buffers is that we used to pass the accessor, but in the SYCL 2020 specification, we actually just, we don't have to create the accessor first. We just pass the buffer directly. And plus we do have to pass in the handler so that it knows which device it's applicable to, right? So these are the main differences in the compiler in the latest release of the oneAPI toolkits and the compiler that's available. So these changes have been made. So if you have been working on data parallel C++ over the last 2 years, you do have to make sure that you make these changes for your code to actually work, right? Yeah, and again, reductions in SYCL 2020, one of the new things that came up was you can now do multiple reductions in the same kernel, and that's what you can see here. We have parallel for, and then we have defined 2 different reduction objects, and then we can pass both the reduction objects to do mainly like 2 reduction computations with just 1 kernel. So that's something also new that was introduced in the SYCL 2020 specification. So with that, so that was the introduction, about the compiler and what changes have been out recently. And with that, next, we'll mainly move on to the hands-on portion of this series. So to get started, mainly, we will do all of the coding on the Intel DevCloud. Please make sure you have an account registered and available. If you are not registered, you can start the process right now. Because mainly it will get all the toolkits available and you can directly start coding. You can also get all the toolkits and all the content at this link. You can download the toolkits and install on your own hardware as well. But if you don't have a system set up, you can always sign up for a DevCloud account and then start coding there. right? So mainly DevCloud mainly it takes less than a minute to get started to code. No hardware acquisition necessary. There's no download or install and configuration you need to do. So most of the samples are readily available. So all you have to do is like sign up for an account, and then you can get started, right? Um, so with that, to get started, so these are the steps you need to take. So I'll leave this on the screen for a bit. Mainly, you have to log into DevCloud or register for a new account. So mainly, you have to go to devcloud.intel.com/oneAPI. So once you're in there, sign in or sign up for a new account. It should take about a minute to complete the process. If you already have an account, the next thing is to go to Get Started and then launch the Jupyter Lab option. And then after that, I'll walk you through. So with that, let me switch over to my DevCloud account here. So give me a second. So if you go to devcloud.intel.com/oneAPI, so this is the screen you should be looking at, and there will be a sign in option. So I've already signed in. So once you've signed in, you can get access to all the details about all the different hardware that's available, all the CPUs and GPUs, FPGAs that's available for you, and what kind of access you can get, right? So how much storage, and by default, you'll get 120 days of access. And you can also set up SSH configuration, or you can just use the Jupyter option, which is more interactive. So that's what we will be using for training purpose, but I will actually show you both the SSH configuration as well as Jupyter. So if you're at this point and logged in, so go ahead and click on Get Started. And once you click Get Started, so you'll get linked to all the different resources about all the different tools and samples that you can access. So what we will do is like scroll all the way to the bottom, and then you'll have an option to launch Jupyter. So this is what we will click on. So if you click on this one, this should load in a few seconds, and then you will see something like this screen right here, right? So, right, so you should see your home directory here, and you'll have a bunch of folders pre-populated here, and you have option to open a terminal and or create a new notebook and so on, right? So hopefully you're able to see this, the list of these training courses here. Mainly the ones we will be accessing today is the DPCPP performance portability. So if you're not seeing this option, don't worry about it. It could be because you have registered for the DevCloud a while ago. You may not have the latest content, but we will show you how to get the latest content. But you can see that we have a bunch of different training content here, specific training content for MKL, and we also have this oneAPI Essentials that I was talking about. So this is the basics, how to get started with data parallel C++. So mainly if you are not seeing this DPCPP performance portability in your list, so here's what you have to do. Click on the terminal that you see here. So you can either just double click on this terminal, and this should open up a command prompt in a few seconds. So once you have the command option, so the content is actually stored in one of the folders in the DevCloud. So we have to copy that. So there's a script to copy that. So what we'll do is like go data oneAPI underscore workshop, and then there's a script called get Jupyter notebooks, right? So if you run the script, this will actually copy a bunch of files into your home directory, right? So I will copy this this command and then paste it in the chat window, right? So this is the command you have to type in either if you're using DevCloud or if you have direct SSH connection. It's the same script. Just run the script and then it should copy, and then within a few seconds you should actually see this new folder called DPCPP performance portability. Right. So once that is done, so we can actually access this folder here. Right. So once we go into the performance portability folder, you can see that there are a few Jupyter notebooks, a bunch of scripts and folders where we have the source code. So what we will do is we will start with the introduction module. So mainly in this first session, we will mainly cover the first two modules here, the introduction, and then the second one is Math Kernel Library, and then basic gem. So if you double click on the introduction module, so mainly this will have the course material, mainly talking about performance portability. And this same Jupyter document has the source code that you can edit and compile directly from this interactive interface, right? So you can either use this, or I will also show you how to run the code in command line as well. Right? So to mainly get started about performance portability and productivity, so we will try to understand what we mean by performance portability and productivity, right? So mainly we will, define performance as some, measurable quantity representing a characteristics of an application. So this could be either the execution time of the entire application, or it could be like the execution time of the actual computation you're doing. So that is what we will define as performance. Portability we define as the ability of an application to run correctly on different platforms, right? So if you write the code in data file or C++, and you should be able to get the same result on whether you're running on a CPU or on a GPU. That's what we mean by portability. And productivity is mainly the ratio of application code output to invest to the invested development effort, right? So this is mainly the amount of effort you're putting to write the code so that it runs on different platforms, whether you're writing for CPU or GPU. Ultimately, you want to minimize the amount of specific code that you're writing for every different platform. So mainly with this definition, we want to, our ultimate goal is to achieve performance portability across different platforms. So whether you've written a piece of code, you want it to run with the good performance, whether you're running on CPU or GPU or any other accelerator, and without making a lot of device-specific changes. So that's what we will try to achieve in this learning series. And we will make use of a bunch of tools to do the analysis, like the vTune profiler, and we will also use the Intel Advisor Roofline to look at different analysis points, right? So like I mentioned previously, this will be based on data parallel C++, and we do have a data parallel C++ essentials series that's available for people who are not familiar with data parallel C++. You can start learning data parallel C++ using the series. So if you want to get access to that, just go back to your home folder here on the left-hand side, and you will see a folder called oneAPI Essentials. And if we click on the welcome file here, you can see the contents of this one. We start with introduction to oneAPI and data parallel C++. We will look at some program structure for data parallel C++. We look at individual features like what is unified shared memory, subgroups. We will look at some tools, Intel Advisor and vTune. We will look at the data parallel C++ library, reductions, more advanced content for buffers and accessors, SYCL task scheduling and data dependency, and also the debugger, right? So this is mainly for somebody new to heterogeneous computing. So this is a good place to start with. You can access this in your DevCloud. So we are mainly assuming people here are familiar with data parallel C++, and this series is mainly focused on performance portability, right? So if you're not familiar with data parallel C++, we won't be doing a whole lot in today's um, today's session. So you will still have time to come up to speed between now and next month's session, which is mostly focused on performance tuning. So today's session will be mostly kind of a beginner approach for data parallel C++. So you should still be able to follow today's session, right? But then please go through the essential series if you want to get up to speed on data parallel C++. Right. And mainly, we also have documentation in this introduction notebook talking about programming challenges. This is what I showed in the slides, and what are the oneAPI programming models, and also the applications and tools, right? So mainly, I will skip through this section. So this is the same stuff that I showed in the slides earlier before. Talks about what is data parallel C++ and how it extends the SYCL 2020 standard, and mainly talks about the programming model, right? I'll skip through this section and mainly jump to this section where we talk about mainly the test application we will be using in this workshop for performance portability, right? So we wanted to pick an algorithm that is something that is easy to understand, and at the same time we can that is actually computationally intense, that we can run on GPUs and CPUs, right? So one of the algorithms we are going to use today is the general matrix multiplication, because we know that it's easy to understand. Almost everybody knows how matrix multiplication works, and at the same time, if we start increasing the size of these matrices, it could be computationally intense, and we can actually capture some numbers and then analyze using the roofline as well as in vTune Profiler, right? So mainly the basic matrix multiplication, mainly you multiply the row with the column of the second matrix, and then that's how you get the output of the multiplication output for the matrix, right? So this is the code that we'll be writing, and the platforms that we will be using is that I mentioned before, mainly two GPUs and then two CPUs. It's the Intel Gen integrated graphics, and then we will use the Iris Xe Max discrete graphics, and then we will use two Xeon processors. So for every code that we develop, we will capture the results on all these four platforms, and then try to see what kind of performance numbers we are getting, right? So mainly next we will talk about the code structure that we will be using for development of this application. So mainly we will be writing a basic algorithm, and then we will be doing mainly optimizations to improve performance step by step, right? So for that purpose, what we are doing is the main matrix multiplication logic, which is your kernel computation logic code, right? So that will be separated out from the rest of the common code. The kernel computation, we will keep it in a separate file, and all the common code will be in a different file, right? So the common code is mainly designed so that we can input the matrix dimension, so that we can test a bunch of different matrix sizes, and then we will also have an option to input like the workgroup size. We will discuss more about that. So that's another input to the application, and then so that we can set various parameters to see how it impacts the performance, right? So the actual code for matrix multiplication is in a separate source file. and then the common code will be in a separate source file. And then let's look at, we also, calculate the execution time um, for the matrix multiplication kernel that is offloaded. And the common code is available here. It's in the source directory, and then it's called the mmdpcpp common code, right? So if you click on this cell right here and run this cell, this should actually print out the code, the common code, right? So let's quickly analyze. So this will be common, for all the different optimizations we will be using. So what this common code does is it mainly, we use this get opt uh, to set up our program so that it takes command line arguments for the matrix size, which is n, and then the workgroup size, which is m. And then we also have these parameters if you want to verify the output with series computation on the CPU, and also an option to like print out the output matrix, right? So these two options you need to be careful, because especially if you start using very large matrix sizes like 1024, you don't want to enable verification, because the verification is done against a series computation on the CPU, which will take a long time, and also printing out, right? So you don't want to be printing out when the matrix size is like 1024 by 1024. But mainly these two parameters, n and m, is what we will be changing. Um, so that's what we define here to identify if there's any command line arguments, and then parse that, right? And then we have the code to define the vectors for the matrix. So mainly size n times n. We define 4 matrices here. So the input matrix are A and B, and C is the output matrix. We also have a D matrix. This is mainly used for verification, right? So we compare C and D will be computed on the CPU, and C is the optimized code that the optimized kernel is generating, this matrix C, right? And we also initialize the matrix with some initial values, some random values here, and we initialize the output matrix with values of 0. Right, and then the main heterogeneous computing code, the SYCL code, we define a queue, right? So this is how we know which hardware the actual kernel code will be offloaded to. So since we are not defining any selector, either CPU or GPU selector, it uses the default selector, which means that if it finds a GPU on the system, it will run on a GPU. If there is no GPU, it will fall back and run on the CPU, right? So, and we also print out the device that it's running on, depending on what device it's selected. So this is just for our reference to know where our code is actually running. And we also print out one of the other device characteristics, which is the maximum workgroup size. So this will become important eventually. So that's why we just print it out, so that at any point we know what's the device it's running on and what's the maximum workgroup size, right? And then the next set of lines, you can see these 3 lines, right? So mainly what we do is we start a timer. So this is how we are measuring the time it takes to run the computation. So we start the clock and get a timestamp, right? And then immediately after that, we call this function the kernel. So this is the main computation. So the code for this function will be in a different file. So this is what we will be focusing on looking at going forward, right? So we will be optimizing that. And then once that function is completed, we again get the timestamp, and then get the end time minus start time, and then we get the duration, right? So this is just for a reference. We use this as one of the metric to measure what is the time it took to complete the matrix multiplication computation, right? And then we have some more common code, which is mainly to print out the actual matrix. And then we also have code to actually verify, do a local compare to see if the actual verification. So we won't be using any of this one because we have already compared that the code is working and the results are good. So mainly we are focused on the actual execution time, right? So this number that we will be capturing. So this is the common code, and we will be using this to compile with the actual kernel code that we will be developing eventually, right? And next, let's look at the kind of analysis we will be doing. So mainly, once we get the code up and running, we will be using two tools, which is the Intel Advisor Roofline and the Intel vTune Profiler. So we have some details about how to use this tools and what this tool does here. This is something we also have advanced topics for each one of these tools that you can refer to. All that code and then documentation is available right here in the DevCloud. We mainly give all the different command lines that can be used to get the advisor roofline report, right? So we will be going into more details when we start actual implementation of the algorithm. But in a snapshot, so mainly what this Intel Advisor roofline does is will generate a roofline chart report. And then what this mainly gives you is gives you a snapshot of what how much performance headroom there is for each group. It'll actually show you the likely bottlenecks, and also it suggests some of next steps, right? So what kind of performance tuning can be done, and you can in detail analyze how much SLM is used, and then the L3 cache, and all the details. So we will be looking at a live graph and then analyzing this eventually, right? Mostly in the next session, the one in next month. So then you'll get a more idea about how to set up the command line and run it. So we also provide links right here where you can click off and then read more about this Intel Advisor tool, get more information there. And same thing with Intel vTune Profiler, right? So what we will do is we will use command line option to capture all the data, profiling data, and we will analyze whatever is possible using the command line option. And once you've done that, you can also use the same data that you've captured. You can open it into vTune Profiler application on your Windows or Linux machine, and analyze most of the advanced features. So we will do that as well, right? And this documentation here also shows more about all the other results that will be shown in vTune. Mainly in case of GPU, it will show you how many EUs were installed or how many EUs were idle, the FPU utilization, the occupancy, and so on, right? So that's about mostly the introduction topic, right? So this is what we will be doing in this learning series. So when you guys have time, please feel free to go through this documentation, and this will give you an idea about what's the approach we'll be taking further, right? So with that, let me close this notebook and then open the second module here. So mainly what we will do now as a next step is we will look at Math Kernel Library. So this is one of the libraries that's available for heterogeneous computing. We'll look at implementing the matrix multiplication using the Math Kernel Library. And then we will also implement using just SYCL programming, right? So in its very basic form. So that way you'll get an idea about how the performance looks when you use a library versus when you start writing your code from scratch, right? So that's the main goal of today's session. And once we have these two accomplished, the next sessions will mainly focus on optimizing for performance, which will be a lot more interesting. So with that, a little introduction about Math Kernel Library. So Intel has had this Math Kernel library for CPUs for a long time. So with oneAPI, mainly this Math Kernel library is extended to work on any accelerator, right? So you can use the same Math Kernel library for CPUs as well as for GPU offload as well, right? So there is a bunch of different library functions that are available for linear algebra like BLAS or fast Fourier transforms and so on. So there's quite a big topic. We have a whole separate learning series for Math Kernel Library that you can refer. Again, also available in the DevCloud. So you can, if you want more details about it, you can refer it there. But in today's session, we will mainly focus on the Math Kernel Library and the linear algebra, the gem function that is available, right? So there is a direct gem function that's available in Math Kernel Library that will take the input and output matrix and then will directly give you the output in which is already optimized for you. So all you have to do is like have this like one command and this will actually give you the output, right? So to understand that, so let's look at the implementation, right? So I told you in the previous module, so let me open that again. We had looked at the common code, right? So we had this common code and in the actual like Math Kernel implementation, we actually have the main function, which is the kernel. So this is the kernel function. This is what will be the main logic for computation, right? So this, along with the common code, is what will be used to compile and then get your results, right? So this document here shows you the steps you need to follow to compile and run. So the first step is, we have a bunch of accelerator selection script here, which will give you a widget, which will allow you to select a device you want to compile and run this code, right? So we have the two GPUs, Gen 9 and then IO6E Max, and then we have two Xeon CPUs. So you can select any one of these. For not to start with, I will keep it on Gen 9, right? So, and then there is the actual kernel code here. So let's do a quick code walkthrough here. You can see that this function takes the input, we get the Q, and then we have the three matrices, right? The input matrix A and the matrix B, and then we have the matrix C, which is the output, and then also the size and the workgroup size of the matrix, right? So since we have a three matrix, we create buffers for the three matrix, buffer A, B, and C, and then we set up these parameters for the MKL gem library that's required, and then all we have is like this one line of code, right, which will do your actual matrix multiplication computation, right? So we do that, and then once you notice that we are also passing in the queue, right? So that this is how the library actually knows which device this code is actually going to be run on, right? So depending on which device is being selected, so that's the algorithm that will be applied, right? And then and finally we have a host accessor. This will actually copy the data from the accelerator device back to the host, and then that's the end of your actual kernel function. So now if we compile this function, this code, we should see the result. So this will actually compile and run on whatever device you've selected here. So the way we do it here is we have a build and run section, and then we have a script written which will compile and then execute the code, which is mainly the run MKL shell script. And one thing we do here is we don't directly run it on run the script directly. We actually run it, we wrap it using this Q script. What this Q script will do is this will actually do the job of running the script on the device that you want to run it on, right? This device.value is based on what device you select here, right? So whether you're planning to run it on CPU or GPU, so that's the code that will be run. So this whole code will be executed. So if you want to look at what's in the run script, let me open that. So if you click on this run MKL script, you can see that we just initialize some environment variables here. And then we have some command line arguments for the actual binary. And you can see that we compile. And this is the command we are using to compile the MKL script. You can see that we have two pieces of C files. One is the common code, right? And then the second one is the actual kernel code. So we compile both of them, and then we have a bunch of MKL related uh, command line arguments for the compiler arguments. And then finally, we create a binary, which is MMDPCPP MKL, right? So, and then the next step we do is actually run the code. We run the actual binary along with the argument, right? So the argument in this case is all we are telling is like use matrix size of 1024. So there are two options. You can compile this one. So either you can open up a terminal. So in my case, I've opened up a terminal here, right? So you can go into a directory to performance portability, and we readily have these scripts available, so you can um, run the script directly. So what this will do is this will run on whatever system you're logged into, right? So whatever system you have currently. So this may not have a GPU, right? So if you want to see what is the configuration of this login prompt here, just do a CL info, and you can actually see details about what hardware you have, and you can see that this particular system has a FPGA emulation device. It has a Intel Xeon Gold CPU that we had listed. So this is one of the CPUs we will be running the code on, and then looks like this particular device does not have a GPU, right? So if you have to run it on a GPU, so you do have to use our PBS node system to first log in interactively on a GPU node, and then we have to compile and run, right? So to avoid all these complications, so we have written this queue script and run script, which will mainly automatically do that for you, which will make it easy, right? So all you have to do is like select which device you want to run it on, and you can compile it, right? So one thing to note is that in some cases you may not get access to these systems immediately because there are a limited number of uh, these systems. For example, Gen 9, we have a lot of systems, so all of you should be able to run on that one. The Iris Xe Max discrete GPU, I think we only have about 13 systems. So if all of you are trying to access that, not everybody will get it. So even if you don't get it, so you will be queued, and then eventually your code will run and get you the results back. But then it may not be available unless you log in interactively, right? So even if you request, it might take some time. Same thing with the two CPUs we have, the Xeon CPU 6128. So we have a lot of these CPUs on DevCloud, so you should be able to get it easily. So this is the default system, right? So when you open up a terminal, this is the default system that's available to you. And same thing with this more powerful Xeon. We don't have a lot of these systems on the DevCloud, so if you try to get access to this one, you may not always get it. So if you don't get access during this session, you can try it once you get home at a different time, right? So eventually you should be able to run on all these systems. So let's try to compile and run it directly on this Jupyter notebook, and I will also show you how to run it directly using command line, right? So to run this code, so Since we didn't make any changes, we don't have to run the cell. If you made some changes here, all you have to do is like hit play, which will run and mainly write the file, right? So once the file is written, then we can run this script here, which will mainly compile and run on the device that you've selected. So we have selected Gen 9, and let's run this one and see uh, if we can get a result here, right? So the reason it's taking time here is because what it's trying to do is like it's taking the script and then trying to find a node which has Gen 9 GPU, and it will schedule it on that system and then get back the results. So it's mainly done that, and then we try to get back the results within 60 seconds. If it doesn't get you the result within 60 seconds, you just have to, it'll time out, but you can still wait, and then it will generate a file for you with the output. So that's what we're looking at. Since these uh, algorithms are not very simple, and we are using like large matrix sizes, so this might actually take more than 60 seconds. So we might have to wait a little bit longer for the result. So if you do want to see the results immediately, so you do have to log in interactively, right? So you can see that it submitted the work, and then it tried to get back the results within 60 seconds. It could not get it, and then it just saying that, hey, watch out for this file, right? So this file will be generated in your directory eventually, and then once that file is generated, that file will add the output, right? So that file should be generated in your home directory right here. So let me refresh and see if we see it. So eventually, since we have so many people, it might be taking a long time to run, but eventually you should see it. So if you want to run this directly in command line, so we can do that as well. So what we will do is like first, um, since I already have a terminal here, let me run directly here. So what I can do is like just run the script, MKL, right? So we just notice that this particular system has only a CPU. So the result we will be getting here will be compiled and run on the CPU. So let's give it a few seconds. So here you should see results more instantly than in Jupyter Notebook, because which is on the other case, it was submitting to a queue, which will take much longer. So here you can see that the program was compiled and executed, and you can see we print out which device the computation was run on, which is the Xeon Gold 6128. It shows you the workgroup size, and then it shows you what's the matrix size multiplication that was done, and then it gives you the compute duration, right, for the kernel, which was 0.07 seconds. And it also prints out the very first element of the matrix output, right, by default. So this is one way to compile and execute. So going forward, if you want to, so the result for this is stored in the lab directory, I think. So if you want to just run with different parameters, so you can directly go to labs folder and then do MKL and put in the matrix sizes, right? So you can, instead of 1028, you can actually do 2000 by 2000, and you can see that we get different results, right? So once you've compiled, you have the binary, and you can start trying out any matrix size you want, right? So we can also check large numbers like 10K by 10K. So this will take much longer. I can see that this was 0.07, 0.09, and then this should take like a few seconds to actually run this one, right? So this one takes like 11 seconds to run. So in all these cases, we were running on the Intel Xeon Gold's CPU. So if you want to run interactively on a GPU, what you can do is go into your login prompt and then try to get a node that is GPU. So the way we do it is the command to do that is right here. So gen 9, right? So if you use this command, so you guys will be able to get a system with so let me copy this and paste it on the chat window if you want to try this out. Um, so you can do Q sub and then uppercase I will saying that it's an interactive mode, and then we are telling we want a Gen 9 GPU system, right? So if you run this script, you should be able to get a node depending on the availability, right? So if you run it, it might take some time for you to get it. So I think I had already uh, got an interactive node in earlier in the session. So you can see that if you actually run this command, you will get switched to a different node, right? And then if you do CLN4 here, um, this will give you all the devices that's available on this particular platform. And here you can see that we have a graphics device, right? So this is the Gen 9 integrated GPU. And also, if you want to find out about the details of the CPU, we have a different CPU here, the Intel Xeon 2176 CPU. All right, so and then we also have a FPGA emulation device on this one. So once we've gotten a GPU device, so again, you can go into the folder, performance portability, and then you can run the script, which is mkl.sh. So this will now compile and then run, right? And then let's look at the difference in results, right? So if you're not able to get this interactive node, it's probably because a lot of people are accessing these nodes, or it's not available at the moment because we have a lot of people in this session. So feel free to, make a note of this command and then try it out at a later point, right? So between now and the next month's series, you can try this out. You can see that we did get a result here. You can see that the offload device in this case is the UHD graphics P630. So this is the Gen 9 graphics device, and it also prints out the maximum workgroup size. And then it shows you what matrix size, and then it tells you how long it took to do this matrix multiplication, right? So it took like 1.3 seconds. So in compared to the previous runs, we actually compiled it on Xeon CPU directly, and then you can see that we have different numbers here. So this way we can uh, test and collect all these numbers. For most of our to do the final analysis, we actually tried all these with a matrix size of 20K by 20K, right? Which is a very large matrix size, and which actually takes like I don't know, up to, in some cases, like I think 20, 30, 40 seconds to do the computation. So we won't be doing such large matrices right now. But we will look at the results that we got from those computations. So for now, we will just compile with smaller matrix sizes just to get a feel for how it compiles and runs, right? So far we've done with this Xeon Gold CPU, and then we tried it with Intel Gen 9 graphics. So we can also try with the other graphics device, right? Which is the Iris Xe Max. So I've actually logged in to an Iris Xe Max node already here. So I'll copy and paste this command again in the chat window. So whenever you get a chance, you can try this out. So let me copy. Okay, let me copy this. So it should be in your chat window. So if you run this command, so this will get access to like a discrete GPU node, right? So if you want to see the information, you can see that we logged into a different node here and just do CL info. And then this will give us the hardware details, right? Um, so you can see that the hardware on this particular system is Intel Iris Xe Max graphics device. It gives you the frequency it's running at, work group size, and all the information, right? And also the number of compute units, right? So these are the on the Intel architecture, the number of EUs that we have. Um, and we can also look at what CPU this one has. You can see that the CPU is the Intel Core CPU. Um, so since we know that, so we can go ahead and then run the same code on this GPU as well. So I'll go into the performance portability folder and then just run the script, which is run mkl. So it will be interesting to see the results, right? So because this is an actual discrete graphics. So we did get some kind of error here saying that runtime error, incompatible OpenCL version, some kind of error. So somebody asked a question, is there a way to see the device specs without just see the devices, right? I think you can do CL info -L. And if you just do that, it'll actually print out just the devices, right? So you can see that it shows that it has a HPG emulation device. It has like one CPU, and then it has two Iris Xe graphics device, right? So this is actually a dual core graphics device. Um, So I did get like some kind of incompatible error. So I'll have to go back and look at it, whether this particular system is not updated or something going on here. Yeah, I think it is right because the compiler is still on like the older version on this particular system. So we may not be able to run on this one currently. Mm. So in general, so we at least got access to like one GPU on one CPU, and we are able to see the results, right? So this is what we will be doing for all the different algorithm implementations, trying to get the performance numbers for each and every platform for every implementation we have. And then towards the end of this learning series, we should be able to compare everything um, and then see what kind of conclusions we can come with and what kind of optimizations we can do, right? So far you have looked at how to run the code and look at the documentation in Jupyter, and we also used the terminal within Jupyter to um, run the code, and we also looked at how to switch to a different hardware device and then compile and run your code, right? For some of you who don't want to use Jupyter, who have set up the direct SSH connection, let me quickly do a demo of that as well. So I'm using this the Ubuntu WSL, and I've set up in the documentation here. You will have documentation for how to set up SSH connection when you log in. It's a bunch of scripts that you have to run, and then you'll have your setup. So if you set up that, so all you have to do in your terminal window is do just SSH DevCloud. right? And then this should log you into into the DevCloud. So this will be same as like whatever you're seeing on the screen here, right? So if you just do a ls, you will see that you will see the same folders that are available right here on your DevCloud. So you can also use this way. I think most of you are more comfortable using just a command line. So you can also access DevCloud using this command line. So if you want to access the same folder, it's the same way. Go to performance portability, and then you can try to access a login node. So you can look at the source code here as well. Right? So you can look at the source code and compile and run and so on, right? So you can, if you want to compile, so go to lab folder, and then I can do dpcpp, and then also include the common file, right? So this is the most simplest form to compile. So I think you have to input a lot of different compiler flags as well. So I'll wait for it, and then I'll actually show you a different example here, right? So let me go back to DevCloud. Uh, yeah. So let's now that we've looked at the Math Kernel Library example, so let's move on to the next section. So what we've also done is, you know, we've captured all the roofline reports and vTune results, right? So if you run these um, commands, wait, let's see. So this should actually generate a tab the result for all the different output for vTune, for example. So we have, if you use the command line vTune, so to do a vTune profile, so we will get a report like this, a simple report. So, but if you want detailed analysis, you can install vTune on your local computer and then copy the results to your computer and then analyze that, right? So, but at least just using command line, you should be able to get reports like these. In this case, you can see that it shows you for a matrix size of 1024 by 1024, it shows you how long it took to complete the entire computation and how much time was actually spent on the GPU for computation, right? And it gives you basic stats about how many EU are installed or idle, right? And then the L3 bandwidth bond is like 32%. FPU utilization is 75%, right? So it gives you basic stats, uh, which will help you to make a determination into how good the performance is, how much headroom there is left, and so on, right? So you can see that there is also the GPU spec available here, what kind of GPU we are using, right? So you can do detailed analysis. So these roofline reports did not show up here. Okay, let me do one thing. Let me directly access it from the roofline folder here. So this is a folder where we have saved all the roofline reports that we have generated. So if you do want to get the roofline report for, let's say, MKL, right? So let's look at this one. You will see that you will get a roofline report here, and we can actually enable the L3 and then SLM, and then see how our how much headroom is left. If you just hover over these red dots, it'll um, tell you how much memory traffic was used, and the performance in GFLOPS, and same thing here, right? So it will tell you the memory traffic, and this is one of useful way to um, get analysis. So what we've done is like we collected a bunch of initial results, roofline reports for various different matrix sizes, and then the algorithm, right? So the name should be pretty obvious. It tells you which GPU it was run on, which matrix size, and then which algorithm was used, right? So we've collected all this information and it's available here, but you can also use the command line to run these reports manually on your system, right? So if you look at the scripts on the left-hand side here, uh, just like we have the run scripts to compile and run, we also have the run scripts to do roofline analysis and also for VTune analysis, right? So there's this roofline script. So the way it works is all you have to do is just put the binary name here. In this case, it's like MKL, uh, and then select which device you're running on, and then what's the matrix size you're using, right? So if you want to quickly try this, so let's run like a smaller matrix, and then since we have a Gen 9 node, let's try to run it on Gen 9, and the matrix size, lab folder, and MKL, right? So we save this file, go back to my node with Gen 9. So what I can do here is like I can do run, no, roofline underscore all. Oh, no such directory. Okay, it's fine. I think it will create a directory. So what it's doing is it's actually running and then capturing some data, right? So you can see that there was a folder created called roofline underscore data, and then uh, analysis is being done. No data was collected for some reason. Let's try this on a different machine. Oh no. It says the workload was too small. Maybe let's try to change this to a bigger number. Some kind of error. Let's come back to this one, maybe on the next algorithm. So let's move on to the matrix multiplication with basic gem. So now that we've looked at running this example with using Math Kernel Library, so let's the next step what we were planning to do is instead of using the library, let's try to write the actual algorithm from scratch, right? So in this case, we will use the same common code that we showed earlier, but then just the function that does the computation is where we will just use the SYCL basics of SYCL that we know, and then write a kernel code, right? So the code for that, just let's do a quick code review of that. Again, this particular kernel function will take in inputs matrix A, B, and C, and we create buffers for A, B, and C, right? And once we create, we actually have to submit this command groups to the device. And the way we do it is using a queue submit. And the first step we have to do is like create 3 accessors, and the first 2 are the input matrices, which is read only, and then we have a write only access method for the accessor. And then we have our actual parallel for kernel submission, and you can see that we define the range, and then we get the item. Since this is a 2-dimensional array, we specify it's a 2-dimensional um, range, and then we get the actual index, right? Uh, for each one of the work items. And then the way we do matrix multiplication, the most simplest form is just have a for loop here, and then just do aggregate all the results into C. where we multiply each work item um, with A and B. So this should actually get you the matrix multiplication result. And one of the other thing we do here is uh, when we define the queue in the common code, we actually enable the profiling info, so we can actually compute the actual kernel execution time as well. So we get like two different parameters that we are capturing. One is the actual kernel profiling time, and then if you look at the common code, you can see that we also have another metric, which is the computation time, which is actual timestamps before and after the actual kernel execution. So the way we enable that one was by when you're defining your kernel, if you have this property queue enable profiling, so this will give you access to uh, the command end and command start time, right? So then you can actually calculate your actual kernel execution duration without actually taking into consideration how much time it took for memory transfer between the host and the device, right? So so let's run this code example. So again, here we can do device selector, and then we will calculate, execute this device, and then we can run this code right here to get the results, or you can actually, so let's try to run it here on Jupyter Notebook, but to run it on different devices, I think we will also run it on the individual nodes that we've acquired, right? So in this case, let's look at the run script that we have, which is run basic, right? So again, we are using a matrix size of 1024, and when we are doing a simple compile and run, right? So let's do run matrix multiplication basic. So if you just run it, so this is on the CPU, and then this will be on the GPU. So let's run basic. So let's wait for results on both of them. So we already got the results for the CPU, and you can see that the matrix size is 1024 by 1024, and we have the two times, right? So we have the actual computation time, which is computed using the timestamps before and after the kernel function, and then this is actually the kernel execution time using the profiling timing, right? Just the computation versus the entire submission. And you can compare this with on the GPU, for example, and you can see that we get slightly different numbers here. The computation duration is 0.23. So you can, again, here, you can try different matrix size. You can try 2048, for example, and then see how long it takes, right? So so this is how we've actually computed for different matrix sizes, is going up to like 20,000, and we have tabulated those numbers, which we will actually compare towards the end. So here you can see that when we implemented using just basic SYCL, obviously it's not performance optimized, it's just a for loop we are using to do the basic math. We get different computation results compared to when we use a library, right? So again, we can look at let's see if we can get this roofline analysis. So here you can see that let me make the screen slightly bigger. So we have computed the roofline reports for Gen 9 as well as DG1, which is your Iris Xe Max, for different matrix sizes, right? Just to give you a comparison as to um, where there is headroom for more improvement and how much memory is being used. So once we start doing more optimizations where we, instead of using more global memory access, if we do more local memory access, you will see that the amount of data transfer is a lot less, and then you will get more performance, right? So this will, all these reports will be more useful once we've done all the optimizations, and then we can compare everything in one snapshot, right? So same thing with vTune profiler results. We have some pre-computed results here that you can look at for different sizes. So you can see that just using thousand size of 1,000 by 1,000 versus 5,000, we see like different times, elapsed time versus the GPU time, and same thing with the FPU utilization and the L3 bandwidth bound, right? So it's a good way to get some numbers, profiling numbers, and then compare, right? So for this example, let's try to go back and try to do one example where we capture the roof line. Let's see if this is possible. So what we wanted to do is instead of MKL, we will do basic, and we will capture this roofline report. So let's try this on the Gen 9 GPU. So if you do roofline, yes, I think there is a question. See that the basic version is much faster than the MKL version. Yeah, I mean, we do see that discrepancy, but then once you start going into much bigger matrix sizes, you will see that MKL will give you a lot of will give you a lot better results, right? And eventually you can see that we will start tuning the code, the basic code, we will start implementing it manually. And then, there is a way to get much higher performance if you tune your code, you know, uh, much, using all the different features, right? Like shared local memory and then trying to optimize for occupancy and stuff. So which is what we will be doing in the next month's session, which is a lot more interesting, right? So you can see that right now we are capturing the roofline analysis, right? Uh, let's leave it at that, and then let's go back to the question somebody asked. Let's try to compare maybe when we're using 10,000 size, right, with Gen 9 basic versus MKL. Do we have 10,000? Okay. Yeah, see, in this case, we're using some Gen 9 10K using MKL. It's completed in like 8 seconds, whereas if you use basic, um, basic is like 157, right? So as and when you scale the size of the matrix, so the basic version, since it's just a for loop, you get worse and worse result, right? So here you can see it's like 3 seconds, 21 seconds, and 157. Whereas in MKL, um, it's like 8 second, 5 second, another 8 second. Same thing with DG1. You can see it's like 2 seconds, 12 seconds, 13 seconds, right? So yeah, so you can try different values for the matrix size. Uh, yeah, and if you have any questions uh, on the performance numbers, yeah, let's discuss. I mean, I want the audience to actually try out different options, different matrix size on different algorithms, and then we can actually compare those in the next session as well, right? So let's go back to this advisor capture, right? So it looks like this entire advisor computation was done here, and you can see that it tells you that in the roofline underscore data directory, all the data was captured. So if you go into this roofline data, you can, one thing you can do is like this advisor tool is also available as a free download. You can download that to your local computer and then copy this entire directory and analyze it. Or this will also generate like HTML options, right? So if you go into report, I think, where is it? 00. Definition. Let's see. E0. So wait, text. Mm, mm. Yeah, so you can go through this these numbers here, right? So it actually gives you what the compute kernel task was, which is our kernel function here, how much time it took, how many active, 82% active, 17% stalled, and number of the EU occupancy is also given here, right? So number of threads started. So you will get a lot of interesting numbers that you can use to analyze these. And I think there should be a HTML file here as well. That's what I'm trying to like look for, which will basically like give you the um, anyway, let's come back to that. So mainly you should be able to get reports, HTML reports like these. For example, like there's one for like basic here. So these HTML reports will give you the actual roofline chart, right? So similarly, you should be able to run like a roof, a vtune report. Okay, so there it is. I think it copies to the main directory here. So the roofline report that we just ran generated a HTML file here. And if you look at this HTML file, it will give you the roofline chart. And in this case, we are not really using SLM, right? So you won't be seeing the actual SLM here, but and then we can compare it with different matrix size as well as different algorithm implementation, and then you can actually see how well your code is performing based on these roofline analysis. There's also a script for vtune here, and again we can do a quick vtune analysis for the basic algorithm, and let's do it on Gen 9 since we have that system. We can do it for 5120 matrix size, so that's good. Everything else should be good. So we are collecting for GPU, right? So if you're collecting for GPU, you can notice that the command line option we're using is GPU hotspots. If you're doing it for CPU, you have to comment out this particular line and then uncomment this one where it captures for CPU, right? So let's save this file and then go back to our node with think this is the one, right? So CL info. So we have a gen graphics here, so we can go ahead and then do the VTune analysis. So this should take a few minutes, and then we will again generate a HTML report, and we can analyze that, right? So once we do that, I think that kind of concludes today's session, right? So mainly what we did was we did two implementations, one using the library, one using just basic SYCL implementation, right? So, and if you start looking at those numbers, you can see that the library will give you uh, a decent performance, right? And then the basic one compared to the MKL version will be less, and that's what we will take it forward and then start doing more optimizations in the next session, uh, using a lot of the SYCL features to optimize the code, and then uh, try to see how we can do right performance portable code. Yeah, I see a message. I get an error running on Roofline. If you can copy paste that. Um, yeah, so I think you're trying to run this Roofline script on a system without a graphics system, right? So the Roofline report is mainly for GPUs. So do a CL info minus L and then see if you are on a node with the GPU, right? Uh, if not, you have to log in to a system with the GPU. The command for that, I think I pasted earlier in the session. Right, so let me go back to the VTune. So it looks like the VTune is still working. Um, okay, so um, let's wait a few more minutes until this is complete, and we will analyze the report. And that will conclude this session, and I will take any questions you may have. And in the next session, I think it should be more interesting because we will work on optimization. So while this is doing, I think I had showed you, um, how to compile on if you're using just SSH, right? So again, here you can directly do dpcpp basic, and then include your common file. Uh, and that's it. And then this should actually compile. the code, right? So all you're doing is like dpcpp and then including the two C files, the actual algorithm code and then the common file. And then I think if you look at the directory, this would have created like an a.out because I didn't specify the output file. So you can just run this a.out, which we are running on a, what do you call, a login node, I think. So maybe it may not run, or let me check the matrix size. Okay. So let's try to get an interactive node on this one. Okay, so the looks like the V2 analysis was just complete, and you can see that when you run this report, you do end up getting right in the command prompt, you do end up getting all the stats here, right? So which will tell you what kind of GPU was used, graphics P630, and then also tells you how much SPU utilization, what was the GPU time versus the actual elapsed time, and so on, right? So, so this would have actually created a HTML report as well. So if you go into the vtune underscore data directory, or did it put it in the main directory? Yeah, you can see that there is a vtune HTML file created in the main directory. So if you click on this one, so this will give you like the vtune analysis, right? So this is something for every implementation. We are capturing uh, the vtune profiling information. So eventually we will look at what we can make sense of that one, the occupancy and utilization, then that is what we will use to optimize your code in the next session. Okay, so with that, we are at the end of this session, and you can see that at the bottom of this module, we do have a lot of resources and links for all the different content you may require. Most of the content is available on DevCloud itself. So if you want more details about MKL or DPC++, feel free to access any of these folders here. So when a lot of people may not have had a chance to log into a Gen 9 node or the Iris Xe Max nodes. So it looks like there was an issue with some of the nodes where the compiler wasn't updated, but that should be fixed soon. And then, between now and the next session, please feel free to, access this module 00 and 01 and try to run the code with different matrix sizes and then see what interesting numbers you're able to capture. And then we will continue this session next month, right? So let me quickly put up the presentation screen here. So let me go back to, right, so this is what we did in the next session. We have the basic algorithm set up, so we will start tuning that, right? So that's where it gets interesting. We will look at some ND range kernel implementation, the impact of workgroup sizes, and then we'll also look at how to optimize memory use, making use private memory and making use of shared local memory to improve performance, right? And at the end of this session, we will have numbers from all the different optimizations and implementations we have, and we can compare it in one graph about what gives you the best performance. And then the third session is even more interesting. This is where we will try to look at all the different hardware characteristics and then try to achieve performance portability across CPUs and GPUs, right? So with that, we are at the end of the session, and then I think there should be a link to a survey. Please feel free to give any feedback. Uh, and I think somebody's asking for the slides. I will give the slides to Ray, and then you should be able to make it available to you, right? So again, yeah, feel free to reach out. My email address is right here if you have any questions between now and the next session, or any other contact you're working with. Um, and we hope to see you next month, right, which is on the 9th of February, and we'll continue there. So thank you, everyone, and I look forward for you in the next session.